Okay, so thanks for inviting me to this semester, for organizing this semester. It's been a good first week for me and our group here. We've been talking about some pretty technical stuff, and this is going to be background material that's relevant to it, but still pretty technical. So if I try to give all the basic definitions, we just won't get anywhere. So hopefully I can give some motivation as we go along, and you can take it, get something out of that. So you're going to have to be looking at things from, unless you're really in the material, you're going to have to be looking at things sort of with a global view and treat it as a kind of popular science, I suppose. Okay, so that's the apology at the beginning. There are papers that this is based on. So if you want the definitions in full, first paper is called Mouse Plays and Suslin Cardinals. And let's see, this appeared in some Singapore volume, I think. It's on my webpage. Okay, that's not sure when it came out. So that's a fairly long paper. This is the joint paper with first. And it was called, I forget the title now.
You go. I think you could too. That was those.
Okay,
Like
so
cardinals and mouse pair limits.
Yeah, okay. Mouse limits and Suslin cardinals, maybe
Something.
one of the other. There used to be notes on work of these two as an article. Authors.
Oh.
This is the other way. Mouse
Limits, yeah.
Thank you. Thank you. Okay, let's both of these on the web page. They're all on the web page. No, they're not. Sorry, these two are on the web page. And then there's one that's called made notes of this and I can't find it. Okay. This one kind of numbers. Hierarchy. It's a typing hierarchy. Well, the projective hierarchy is an example of the type 1 hierarchy. So it's some hierarchy that looks like the projective hierarchy. So this is on the list. This handwritten notes that, and it's not reached the stage of these others because there are a number of open problems that are raised by this thing. So the pattern of connection between the Suslin cardinals and mice It's pretty well known in projective hierarchy, very in great detail. Okay, and then there's some global facts beyond the projective hierarchy, which is the beginning of things in terms of the world. So there are these global things, but sort of when you get to the fine structure of the connection between Suslin cardinals and mice, we know in the projective hierarchy, it's not known at the counterparts of the projective hierarchy at higher levels. And that includes levels of L of R. So there's some nice open problems in trying to draw that connection clearer. Okay, so those are the references. So now let me say what the players in the drama are. So first, mouse pairs. Again, this is just a sketch of the definition. These are pairs of the form. So we usually consider these our background theory, and I think we can just for this talk is just always use AD plus ADR. So we're in a determinacy. Everything is all sets of reals are really nicely behaved. Okay. How is measurable. Okay. So these are pairs of the form P sigma. So if we're in this context, the AD context, usually P is notable, transitive, and ENOS. Either strategy pre-ENOS or extended pre-ENOS. Okay, and on sigma levels, and when I go on, I might as well go on iteration strategy. For the what's a nice one. The main property of sigma has optimization. Okay, let me just draw the picture of that, which will substitute for a definition. We have our structure P. It's a pre-mouse, so I didn't tell you anything about what pre-mice are. They have a hierarchy, a well-ordered hierarchy. They're constructed from objects that you add one at a time. These objects are called extenders. So they represent elementary embeddings whose domain is the pre-mouse, or the amount of the pre-mouse that exists when you put the extender into the model. That's really the domain of this embedding. Okay. There's have other properties, like the alpha power should agree with P up to the image of the critical point and just a little bit past, really up to the place where you put P into the model. P is not in its own ultra power, that would easily give you ill-founded iterations and nonsense. So P is, you agree up to the place where you put E on, and then you're just, okay, so that's the sort of the coherence property of these extenders. So this is a pure extender premise, just constructed from extenders. Another important thing is an iteration strategy for your greenhouse. That's a method of choosing branches of iteration trees. So, I can take the alpha power by E, that's an iteration, take the alpha power by E again, and so on, keep doing that, that's an iteration, direct limits and limit ordinals. The other thing about iteration trees is I could take an ultra power by this E, and then in the ultra power, there might be some F that overlapped the strength of E, which is this place where we put it on. Okay, that F can be applied to the original model, not just the ultra power. Okay, so that leads to the tree structure. But really, the right thing to do in most circumstances is apply this F to the earliest model that you can apply it to. That way you don't sort of lose information. Apply it to this weaker model, the ultra power, you're losing information as you go along, and you're not going to be able to do what you want to do. Okay, so you could have structure like the first thing you did E, but you can do all sorts of stuff. You can back other models, form a tree at a limit ordinal. You have the tree up to lambda, iteration tree, and sigma of the T should be some B that's cofinally named a branch, that's such that the direct limit model is well founded. Okay, so the MBT is the direct limit model, should be well founded. So sigma is a way of continuing at limit ordinals while staying in the realm of well-founded models. That's an iteration strategy. That's what converts your countable completely silly P into a standard object that can be compared with others of its kind, others that have iteration strategies. Okay, so that's what an iteration strategy is. Now, strong Hall condensation says, if I've got this situation and I've got a tree by sigma and another tree, call it S, and I have an embedding from S into T. So I'll have some E called the tree embedding from S into T. So I'm not going to tell you all the details of what a tree embedding is. It's sort of like take this whole system, take a grain of skull and pull of it, but be very careful about how much elementarity you're demanding of your scope. Okay. So if you have that situation, then T by sigma decimals. Okay, so the strategy condenses to itself on the tree. Okay, that's the main property. There are two others which I be a believe it or not, a bit less detailed about. That's 1, 2. Sigma should normalize well. Okay, normalizing is we've got P, we've got a tree T, we've got it has the last model. It's going to be a successor point, but that way. So we got some model here. Okay, we've got a second tree U. which is on in BT. So it's on the last model. Yeah, so I forgot to say, one of the properties of this E is the extenders you use are of increasing strengths. So I'm not allowed to take my F down here below. That's called a non-normal tree. Okay, so that ensures that each model agrees with all the succeeding ones up through the strength of the extender you use. You're never dropping in agreement with the future. So this is normal. So this one's normal. It was normal on the last model, but certainly may not be the case if you just stack the two, it's normal, because these ones could be going back with shorter extenders. Okay. But there's a way of shuffling these extenders into the extenders, which gives you a normal tree. And that's called WTU. This one's normal. And it's, you can make it quite precise. It's a minimal shuffling in a certain sense. All extenders here came from extenders that follow the surround process. There's an algebraic characterization. Okay, so we have our W, it has last mount R. There's an embedding here. Okay, and so these two T and U by sigma okay, so that's normalizing well for stacks of trees and too. You really want it for stacks anyway. Makes sense of that. Okay, so that's the other. There's something called lift consistency, which I don't. Some variants of this. It is sigma is consistent. And then if P is a strategy, P sigma is a strategy. So that is a strategy. Okay, what's that? Well, I sort of explained what an extender is. Constructed sequence of extenders with this coherence problem. But now, if there's an iteration strategy for this thing, that iteration strategy is, we hope, also a canonical object. Okay, and so, as soon as you got this initial segment of the model in your hands, you could start trying to feed in an iteration strategy for it in hierarchy as you go. And that's what a strategy mesh is. It's got information about how to iterate itself being fed in every stage. It sees this initial segment as it went on. It's able to construct certain iteration trees on that initial segment. And then its predicate, the thing you're feeding in to its predicate, is not just the extenders, but which branches of those trees should you choose. Okay. And of course, we want to be feeding in the information that's given by our external strategy in the pair P sigma. So that's called push forward consistency. Okay. Why is it called push forward consistency? it's the general form of it is if it's what sigma. And then each strategy is acted on stacks of trees. That's what I'm talking about, stacks of acted on stacks of normal trees. So I have to talk about the normals. Okay, so there's a strategy that is a strategy for him. And you just look at what, and that's the first element of your stack. So that's called sigma. And I might as well get the general definition. We have some stacked trees. Last model. So S is some vector of trees stacked on it. And last model. The tail strategy sigma S and acts on stacks that are on T. Stack M. And it's just sigma. And we demand that push forward consistency says if S is my sigma, last model M. And we look at in P, we had information, how should I iterate myself? Move that forward to N, it's that pushes forward some information about how to iterate N. And you want it to be consistent with the tail strategy. That is sigma dot, which is the strategy predicate. Then is contained in so that's consistent with the tail strategy. Okay, so those are all the properties of the mouse pair. It can either be a strategy pair, if this is a strategy path, mouse, or it can be okay, so that was that's what a mouse pair is. They have all sorts of nice properties.
What's your about what? What's your
So your language, the language of premise has a predicate symbol for the extender sequence, but then also, if it's a strategy premise, it has a predicate symbol for the strategy. So this is just a symbol as it's interpreted in the iterative. Correct about the external strategy for the main thing is comparison. See the topic. Or extended strategy. Okay, so I got B sigma U lambda U two pairs. And again, our context is AD plus. AD plus, I mean, the important thing here is these were omega one strategies acting on countable stacks, countable trees. Okay, but for comparison, you really need to be able to iterate all the way out to omega one. That is, there's trees of omega one, length omega one, that according to the strategy should have an accountable branch at the end. And for that, you need that the strategies are nice. Otherwise why aren't you getting a narrow and shiny tree? Okay, so you need nice strategies. Being in a model of AD plus, a set of reals in the model of AD plus is like really good. It's nice enough. In particular, omega one's measurable. So if you have like omega one's going to have a branch. Arguing around shiny trees. Or iteration trees is like omega one always have. Okay, so this is actually really important for the whole motivation for descriptive intermodel theory is you should be dealing with strategies that are nice enough to be in and it take you a lot of effort to show that the strategy that you've gotten from whatever process can actually be put in the model of AD. Okay, but we're sort of assuming that's we're in a context where whatever work was just referring to had already been done. Okay, so anyway, given these two things, we can then just compare them actually to a countable pair. Our psi T E and U countable T sigma U lambda. So say that this is the iterate just means that this is the tail strategy of both. So it's T and there's let's say at most one of the branches drops. I have to say that in order to say that this is the same thing. What if this one iterated to initial segment of that one? Well, then there's a drop at the very end. Okay, so we have that kind of comparison. Okay. We also have something called the dye density theorem. Which tells you in particular, so I say that the side that didn't drop came out shorter. So let's say this is the it's going to come shorter. P sigma is less than or equal to star U. The side doesn't drop here. B R P. Okay, so we lost no information going from here to here. This one may have dropped, and hence was, this thing's actually weaker than Q. But this one, R and P have the same information. R is an iterate, and no information has been dropped when we got to it. Okay, so P sigma is been compared with this one and shown to be stronger. It's equal to. Okay, this is called the mouse order. It's called an order because it's a pre-well order. That's part of the Dodge-Jensen lemma. So pre-well order. Another part of the Dodge-Jensen lemma is the minimality of iteration maps. So if I have an iteration of P sigma, by the way, the terminology, the iteration of P sigma is an iteration of P that is by sigma. Okay, so if you have an iteration of P sigma, some R lambda, and this is actually could be some stack. So it's an iteration of that. So it's a stack by sigma. Okay, we have our iteration map here. It's called I sub S. Okay, and suppose you have another embedding, elementary embedding for P. We can call that. Okay. Okay. Which is elementary. What that say? Well, A is a map from P to R. That's elementary in the fine structural sense. We really have just combining all the fine structure. You really quantifier count how elementary the maps are. So anyway, this is elementary at the appropriate level for maps that act on P. Okay, it's elementary, it goes from P to R. And it's elementary as a map on pair, not just on P. What's that mean? The pullback, the K pullback of lambda. Written lambda K. So what's that? K pullback. Lambda defined by lambda K. You can get a tree on P. T is lambda. Take K and use it to push up the tree T. It's called KT. So in other words, if I've got P here, and I've got some tree on it. Okay, P is embedded by K and R. I can just sort of copy this tree. Step by step, like the first step uses the extender E up here. I'm going to use K. Okay, and then that gives me a copy map from the first models, which I can use to continue lifting. So basically, you can just copy a tree under an elementary embedding. That tree is called KT. Push up. Anyway, at T by K. Okay. Now, R had this strategy, so lambda of KT is some branch P. This map on models is just every model here doesn't. So B, the tree order is the identity, the map by the identity. It's just the models that are being pumped up. So MBT here exists over here, and B is equal to okay. Basically, I'm trying to find what it is to be an elementary embedding from a pair to a pair. Elementary on the map, on the premise, and this strategy gets lifted into that strategy. Okay. Okay. Okay, so Di Jensen says the explanations of what the situation was. So we have an elementary map from there. Then the slogan is the iteration map is minimum. That is, first of all, what I really should have said is if this maps to an initial segment of that one, then that initial segment has to be equal to the whole thing. Okay, let me just say that and not write it. Okay, so that's one clause. You cannot elementary embed yourself into a proper initial segment of an iterate. The other thing is this branch can't drop. So again, my diagram kind of assumes because I have this embedding that didn't drop. That's another condition in Di Jensen. And then the final one, if we're actually this diagram does apply, is that the iteration map is minimal. That is, IS of the just as the ordinal should be less than the deployment. Models are well ordered, so just that tells you everything about how the minimality of the map. Okay, so the iteration maps are minimal. Okay. This immediately tells us, what if this is an iteration map too? Maybe not by the same stack. This might be I sub T, some somewhat different normal stack that somehow got to the same less model. Then the embeddings are the same. So iteration maps are unique. They exist at most. Iteration. P sigma to Q to okay. After this, we can find a milestone. As we can take all of the iterates of P sigma, any two of them, we can compare them back together. On Di Jensen, they have to iterate back to the same thing. So we let F for P sigma mouse square. F of P sigma is the collection of all Q lambda. Let's take Q lambda is a non-dropping iterate. Of sigma. Just seeing that if we have P sigma, and this could be by some stack of trees, not just a single tree. By a countable stack. Okay, and we just seen that if we iterate two ways here to Q1, M1, Q2, lambda 2, since they're both mouse equivalent, it's non-dropping, they're both mouse equivalent to the original one, mouse equivalent to each other, which means when you iterate them, they come back to the same R size. Okay, was I1, J1, these are the iteration maps. Okay, well, the composition of iteration maps is iteration map. So that means, and the uniqueness of iteration maps tells you that this top is the same as this bottom one. So we have a commutative system. So I J1 circle I1 J2 circle I2 by that Johnson. And that tells us that we have direct limit. Which I think anyway, M infinity, the sigma, it's direct limit. Makes sense. And there are maps from any point in the system into the direct limit. So we take the Q lambda in this system. Then I and where we put all the symbols, I'm sure. I lambda Q. Actually, I don't need it, right? I lambda phi from Q lambda to infinity is the mean. Into what? Well, what's the strategy for this one? One can make sense of it. Every countable elementary sum model has a strategy which you get by pulling back into the system. I think that's enough sense of this here. It's interested in. Okay, so you have a direct limit system. It's easy to see. M infinity. So P sigma is mouse equivalent to Q lambda. For each is mouse. The other, that just means that when you compare them, they iterate to the same thing and neither side drops. if an owner live, they have the same infinity. The one direction is trivial, the other direction is only slightly less. So if they're mouse equivalent, that means you can compare them and stay in the two systems, and then from the direct limit of the P sigma system is the same as the direct limit of any of its iterates. Okay, so that's one part. If they have the same infinity, you can sort of pull this back by a skull and pull, and then you get basically the iteration into infinity is a kind of comparison, but you want to pull it back into countable trees in the system, which you can do. Okay, so the M infinities, possible M infinities get all the mice in this mouse order. Mouse order is very fine. I mean, every time you increase a quantifier level of the complexity of the mouse, it goes up in the mouse order. So it's extremely fine order. And the M infinities hit them all. Let's see, corollary, each M infinity is ordinally definable. Namely, it's ordinally definable from the place of this thing in the mouse order, which is an ordinal. Okay, so we have, and not only ordinal definable, it's hereditary ordinal definable, because this is P is a well-ordered structure. So you made up by a set of ordinals. Okay, so all of these guys are in odd. And actually, the sequence, alpha goes to H alpha equal to common infinity B sigma or B sigma of minus rank alpha. That function is in time. Okay. So odd knows the sequence of the mass flows. And it turns out if ADR is that's odd. Still of that sequence. Not a very useful way of analyzing odd numbers. Okay, so these mouse limits are connected to odd. A more useful thing is ADR. Introduce odd pair capture. Let me I'll pick up the odd thread later. So that was all introducing mouse pairs. Comparison, some relation to odd. Okay, what about Suslin cardinals? Okay, so this Suslin cardinal. Oh, set A is Captain Suslin. Reals reals for all this in the bare space. We can only have A is the projection of some tree. Omega plus kappa. Nodes of P consist of finite sequences, pairs of finite sequences, S, P. This is finite sequence of natural numbers here. T is a finite sequence from kappa. Okay. Which are closed under initial segment. This if I have a later pair. Yeah, they have the same thing. If I have a later pair, then cut off the two at some earlier length, then that pair is also in the tree. And the projection of T. So we say that an infinite sequence X, if we have a branch to the tree, it gives a pair XF, where X is an infinite sequence of naturals and infinite sequence from kappa. And X is, this is an example of X being in the projection of T. X is in the projection of T if there is some infinite sequence order with such pairs of its initial segments. This is why you care about that. Well, I can, if I've got a T, I can pick a canonical element of that by looking at the leftmost branch of this T and taking the real part. Okay, so I've reduced all the information in our, I don't, it gives you a lot of information about this set A, in particular method of choosing numbers. Okay, so Suslin representation is very important in the determinants. In the determinacy context, we can't pick members of sets of reals unless we have basically a Suslin representation. That's exactly what you need to do the and their theorems to be effective. You can't always being able to uniformize a relation on the reals and having a Suslin representation are basically equivalent. So we're really interested in Suslin representations. They're very valuable in the AD context. They give you sort of maximal information about your set A. Okay, we say the kappa is a Suslin cardinal. If and only if there's a set which is kappa Suslin, but not not lambda Suslin. And strictly less than kappa. So you get a new Suslin set when you reach the order kappa. Answer. S kappa is equal to the function kappa Suslin sets. And so if S kappa is not the union over alpha strictly less than kappa of the S alphas, then kappa is a Suslin cardinal. These S kappas are closed. They're nice point classes. There's notions of complexity in the wage hierarchy. So it's closed down under wage reducibility. And it's also closed under existential quantification of the reals, because if I had a projection if I have a relation on reals, which is kappa Suslin, so there's another there. And then I project on y, well, I can consider this as part of the. Okay, so just rearrange it pretty. Okay, so these are basically all. No, let's say they closed under countable intersection. Yes, union false one exists. Real closure. They're not necessarily closed under for all reals. And they're not closed under complements. Almost any, if kappa is a Suslin cardinal, they're just not closed under complements. Okay, it's some considerable work included, but it's true. That's kappa. That's kappa closed under complements. If you need kappa is not Suslin cardinal. There are two things that go together. This one and the fact that Suslin cardinals are closed. That is so Suslin cardinal is closed. We're going to all give an ordinal subset of data. Okay, this is essentially the characteristic that I think he assumed this, which was later proved. That's how it goes. I know these two facts are true, and I'm pretty sure that's how it went. Eckers proved this modular closure of the Suslin cardinals. The closure of Suslin cardinals and the plus many other things. Okay. So that's our global picture of the Suslin cardinals. Let me, since I haven't, let me close here. Can I have like 5 or 10 minutes? Okay. I want to draw a picture of the projective hierarchy, which is, pattern that I was saying we'd like to generalize at the higher levels. We can't completely. So let's look at the Suslin point classes and how they relate to mouse limits in the projective hierarchy. Okay, so I'm not going to credit things too carefully. The things about the pure descriptive set theory of Suslin cardinals and projective hierarchy is this Moskowakis' work on the periodist, second periodist is really important. Kekris and Martin did some important things that so I guess it's really Martin Kekris and Moskowakis. Yes. In the projective hierarchy, I don't think so. Unless we start relating them to the aleph, which I'm not going to. Yeah, if we relate them to the alephs, then no, I'm just going to do the softer part. So here's a picture of the projective hierarchy. We can start with pi 0, 1 equals pi 1 to 0. If you're Addison, you write it this way, and that's that's illuminating and good. Okay, so here's the zigzag picture, which is 511. So I'm circling the ones that have the order property, but also the scale property is kind of relevant. These S kappa, another fact. Either S kappa or its dual class. That's the scale property. Okay. So these making your way up the Suslin cardinals and making your way up the point classes with the scale property are the same thing. However, this is more, the way the manipulation is more structured. Point classes with the scale. Okay. Okay, so in the projective hierarchy, this one has scale property, and we have signal 1, 2 here. One on, thank you. Signal 1, 2 here, which has the scale property. These are all both ways. And so on. 3, 3. 3. Okay. Well, purple ones have the scale property. Okay. Now we saw that the S kappas are full-face plugged Fs is closed under exist reals. So they have to be on this side. In fact, these are all S kappas, and those are all the Suslin cardinals get these point classes. Okay, so this one is S of the first Suslin cardinal. And what's the first Suslin cardinal? Okay. And what's important part, property of signal 1, 1. Okay. Okay, the next one. Okay, this one has the scale property. The scales are norms, pretty well orderings of my delta 1 ton, which is 1. So this is the pretty well ordering. Okay. So they're all omega 1 Suslin. But the class of all Suslins was this one, which supposedly exists. Is delta 1 equals getting X cards. And we go up to the next Suslin point class. Okay. Well, we can, so the next Suslin cardinal to turns out it's alpha omega. We're going to stop being able to write down the cardinals. And Steve Jackson, that's computed what these cardinals are, but we're not going to, we're just looking at the software thing. So how do you identify a descriptive set here? Theoretically, there's a result of Fjord, and it connects it to Mars. It's the soup of the GMN well orders. Okay, so there's something called the envelope of a point class. So, and that's a self-dual class. Initial segment. So this is, okay, so actually there's an envelope down here. Envelope of signal one. That's the union over the omega n I11 omega means sets. So those are some very low level delta M2 sets. That's beyond this pair, and it's where you get scales for sigma one. Scales, just so every sigma one set has a scale whose individual norms are in this envelope, and that's exactly as far as you need to go to get. You can't get a scale that's norms bounded. And, okay, this thing is just this is the envelope of I want to. And what you do is you just take these sets and you apply a gain quantifier to them. So it's the union over n of G. And then I want this gain quantifier to it. So down here, I gives you typical set up here.
What was the sigma one union per one?
You mean what's this envelope?
Yeah.
I'm not really defining it.
Okay.
It's some class that would take us too long.
Okay.
Well, actually, here I find it. Yeah, okay, I did. It's the union of the omega n pi on one sets. What's an omega? Well, a typical. How do I get beyond here? I could take a difference. Pi on one set minus a sigma one set. That would be a one. Maybe that's a two. So, okay, well, you can iterate differences. You actually can go when you get a board number of steps. Increasing sequence to look at the rings. You take the meaning of those rings. That's typical settings. Okay, so these things very concretely identified. And that's as far as you need to go to get actual scale on the segment. All of the norms should be exactly what we do. And then if we just apply G to that, we get, and that's basically Moskowakis' periodicity. That's Moskowakis' periodicity. This is where you get scales on sigma 2 and pi. You get scales on sigma 1, 2, the norms are all on sigma 2. This has the free will argument. But for pi 1, 2, we have to go further. It doesn't have the scale down. And this is how far you have to go. Okay. Okay, and so kappa 3 is the characterized descriptive set theoretically is, I guess. I'm sorry, just in the notation. This would be envelope 1, this would be envelope 2. So it's the real ordering. That's where you need to go to get two sets, and it works out to be. Or this part. Right, it's alpha omega was proved by. Morton proved that it's alpha. Okay. Then what's kappa 3 is kappa 2 plus. And it's that's Suslin cardinal. Okay. Kappa 4. We can go 3 in the coding method. And if Steve Jackson can tell us what it is, then maybe some megas, something.
Oh, omega times omega.
Mega, maybe mega. No, sorry. What's that?
Don't trust me.
No, okay, so anyway, the point is, that's cardinality omega. So you'll notice so far, we have the regular ones. Let me start here. The regular one, then we have a cardinality omega, and we have another regular one, we have cardinality omega. They alternate that way.
Do you want to write the 3 doing the delta and 3? When you write in V3, do you mean delta in 3?
Yeah, envelope 3 would be.
Like a kappa 4
delta
would be delta. So
Yeah, delta. Yeah, thank you for delta. So then 3. And it's up here somewhere. Okay, and kappa 5. The last one here would be delta 1. Wow. Which works out to be kappa 4 plus. Okay. Okay. So in terms of the S kappas, these were this one was S kappa 2. This is S kappa 3. Right, this is delta 3, which that second one 4 is delta 6. That's 3. Here will be a scaffold. Okay. So that's the pattern of Suslin cardinals and scale point classes in the projected hierarchy. The Suslin cardinals are all being both going on the omega and right. Okay. And what's okay? Where are the mice here? The mouse limits. Well, I should say the end. This is the Greenberg, isn't it? This one, and the higher ones. Yeah, sorry.
It's okay.
No, I shouldn't. Yeah, Art did it for signaling for this envelope. And if there's a connection to mice, and then it can be extended to mice at higher levels, and that can be used to characterize these envelopes in terms of mice, and then you get this. These envelopes can be characterized in terms of iteration. But the higher things is mice, which actually dwarf did too. Okay, so what's the connection to mice? Denotes limits. Okay. So let's start at up here. So I have some more nice. That is, let me start with. Actually, let me start with. Well, actually, it worked for here, but let me start. Let me start with this one. So let's let alpha 3. Sorry, no, I'm starting with this with alpha 2 is the orbital height of m infinity of what? So the model M1. Put at its bottom window cardinal. M1 is or the minimal proper class model with one should look at. And its strategy. It has a canonical strategy, unique strategy. Okay. Okay. So in other words, the wooden cardinal, if you take the direct limit, M2, the delta 1 of M1, that's some kind of ordinal. When you take the direct limit of all iterates, this thing goes up to alpha omega. Because, 2. It has cofinality omega. Why does it have cofinality omega? Well, it started out having cofinality omega, and the iteration maps are all continuous at a regular cardinal. So that's cofinality omega. Okay. Yeah.
There's like an infinity. Yeah. Ordinal.
Right. Yeah, the ordinal. Yeah, sorry. Yeah. The ordinal height of m infinity of 3 knots you're iterating is M1 delta and by its strategy. And actually, you can also characterize the Suslin cardinal kappa 1 this way. What is it? In a way that's going to be completely general. Namely, we look at the least cardinal that's strong to this one. So let image sorry of this P1 by P1 infinity the least strong. Strong to delta 1. And then the cardinality of greater infinity omega 1. Or it's exceeding Suslin cardinal. This is a completely general pattern. That is, the cofinality, the regular ones are given by these betas. The cofinality omega ones are given by the integral unit. So like at the next level, kappa 4 is the ordinal height of infinity of, now I need to take M2. Oh, you're right. Let's see. Kappa 3 is where the first strong number. Kappa 3. Yeah. Kappa 3 is where the first strong to the bottom. M3. But we still always cut at the bottom when we cut stop. So this is delta. Strategy. So that. And Kappa 3 is beta infinity. But then infinity is the least strong to the ordinals here. Just say to Kappa 4 to this ordinal relations. And have it. So even kappas are the images of the wooden, of the bottom wooden cardinal in more and more complicated mouse limits, and the odd ones are the images of the classic. Yeah, in this case, it just works out to be just cardinal. So that's a connection we'd like to see generalized to the higher levels of R. We get a fair amount about how it generalizes, in fact, in general, as far as the mouse pairs go. But not completely.
This is just to make sure. So if I just substitute like n into n+1,
Yeah,
and it's not
yes, yes. This is 2n plus 2 and 2n plus 1.
So in this sense, it doesn't generalize. So
That's right.
in that sense, it doesn't generalize.
Yes, it does.
Let's just project.
Yeah, but then there are hierarchies beyond that.
Sure.
That like even at the next level of LR, the next projective hierarchy, I mean, I think we do know that, but it's was something that wasn't known until a couple, 3 years ago to generalize the mouse set properly. Some facts that we had known about relating mice to mouse capturing in the projective hierarchy, we only had rough forms of it. The next one, we got it down the right thing, and then that then you sort of feed in these ideas, and you get the analysis of the Suslin cardinals in terms of mouse limits at that level. Okay. So, okay, we can do it the first 2 projective or 3 projective hierarchies. It certainly should be able to do it at every level of R, and even should be able to do it as far as the mouse limits go.
So we'll continue tomorrow. Yes.